Hi guys, today I'm doing round 669, div 2, and unfortunately this is in the middle of a school day, which means I have a small gap where this will work, and I'm gonna have to cut the contest short of 5 minutes if I don't finish, which also probably means I won't get the solutions in this video if I don't full solve everything, but I will upload a separate solutions video later after school ends, I guess. For now, I'll just be doing a screencast of my participation. So let's start as always by updating the sub count because it's fun. And we will get started. Did that just jump by 2 seconds? Whoa. Whack. We begin. That is a nice name. Okay, open the problems. I mean, even like the array with zeros and ones. The elements are 1 to n. Alternating sum of the array will be 0. Okay, so the way this works is basically, actually, I'm not going to whip out paint yet. I'll do more elaborate solutions after. But basically, there are going to be at least n over 2 zeros or at least n over 2 ones. Now, what that means is if we take n over 2, oh wait, hang on, how would this work? The problem with okay, let's read in the input. And we have to figure out some way to do this. So if we can make it with all zeros, then I see. So we're going to basically keep track of the counts of zeros and ones, and then either we have at least n over 2 zeros, or we have more than n over 2 ones. So in the first case, the alternating sum of any array of zeros is just 0, so that's fine. And otherwise, we can engineer it so we have an even number of ones, and that way we do have an alternating sum. So if C0 is greater than or equal to n over 2, C out n over 2, that's k, then we'll just print 0. Otherwise, we have at least n over 2 ones. So if C0 is odd, then we can subtract it, and that works because we're still going to have at least n over 2. And then C1, and then we'll do that. Forgot the bracket. And I forgot the test cases. Okay, so we have 1, 0, 1, 0, 2, 0, 1, 2, 0, 0. And 1, all right, 2, 6, wait, okay, 6, 6, 0, 0, 1, 1, 1, 1. Okay, that should work. Yeah. Okay, we go on to B. That may have been slightly overcomplicated, to be honest, but whatever. I mean, we got it, so it's fine. Alexander is a well-known programmer. Today is finally decided to finally go out and play football. With the first hit, he left a dent on the new Rolls Royce of the wealthy businessman Big Boba. Okay, interesting. One of you guys recently opened a store. Okay, so that's just backstory. You're given n positive integers using each of them exactly once, exactly at once, or exactly once. Not a big deal. You have to make such sequence B such that sequence C is lexicographically maximal, where C is the GCD of that. So it's definitely greedy. Greedy works because it's lexicographically maximal. So if there's got to be some like, yeah, there's got to be like if we make a choice that will give us bigger GCDs in the future, but it'll screw us over in the beginning, like we care more about the beginning because it's lexicographically maximal. So we basically want to maximize every element as much as we can. So greedy will work here, I think. And therefore we just we start off with 0 because GCD of 0 and anything is itself. Like GCD of 0 and x is x, and then we'll just go along. Then we'll take n numbers, and we have to look at all numbers every time, so we just do stuff. We brute force. If targ equals -1, targ equals j, else if GCD, RGCD, and AJ is greater than, essentially if we get a better GCD, then we can put that here. If this gives us a better GCD, we'll just take it. Then RGCD equals RGCD and AJ. Cout AJ and that. A targ, my bad. And still. How? What the hell? What is this? What the hell? I guess, this targ equals 1. It's important too. Okay, 5, 2, 8, 2, 1, 3, 9, 3, 8. Yes, 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 perfect. And again, greedy works because we want to maximize lexicographically. Interactive C. Wow. Also, what? Why has nobody solved B yet? Okay. We're doing pretty good then. Alright, good speed, good speed. Let's keep going. We hid from you a permutation P of length N. Okay. We have enough patience to answer almost 2 N queries, so you should fit in this constraint. So I'm assuming the first thing we want to do is find N. If we can find N, then we can take everything else mod N. Or if we can find the position of N, then everything mod N is just itself because N is greater than that number. So like X mod N, where X is less than N, equals X. It just works that way. Yeah, so how do we find N? That is the question. and we have 2n queries. So let's say we have 1, 2, and 3. Okay, so first strategy is to try and find n. However, there may be some other strategies that also work. We need to find n in O of n queries. So there are no test cases. Fine. Then we print, exclamation mark and that. So what? Okay. Okay, I see how to do it. So let's say we have some array like 1, 5, 1, 4, 1. Sorry, let's make a good example. 1, 3, 2, 4, 5. So we start with here. Then let's say we just fix 1. Then we query this one. If the mod we get is itself, then we know that this element is greater than this one. So now let's just set the target to this one, because now we have a greater element than 1. So now we have here, the mod is not itself, so we know this is greater than this. So we know this is greater than this, and therefore we don't take this one. So now we look at this one, 3 mod 4 is 3, so we know 3 is the biggest, so now we take 4, and then we know 4 mod 5 is 4, so now this is the biggest. And if we just keep doing this, we're always going to find n, because we can always take an element if it's bigger. And once we get to n, then nothing's going to be bigger than n, so we'll just keep that index. Okay, so then we do LLV equals query index n I. And we're going to just make this work for 0 indexing. If v equals... Actually, wait. Does that work? Because we need to find the specific value of that. That's kind of annoying. Are we given any value? We need to find the value of the index we start with, actually. And that kind of doesn't work. Okay. I think we can find the value by... Okay, so that's... I'm not actually sure if this idea works, because we need to... Actually, we don't know that this is 4. We just know that it's bigger than whatever this is, and this is bigger than whatever that is. Which is a problem. But we can find the value of 2 integers by saying this, for example. So we can query x and y, and then y and x. And that works because first we get x mod y, which is x if x is less than y, or some number that's less than x otherwise. And then we can also query y mod x. So let's assume that x is less than y. Then here we just get x, because x mod y, if x is less than y, is x. Here we get some number less than x. So we know that because this is the bigger one, x is less than y. And we know, actually, we know the value of x, therefore. So let's just get a single value. But it doesn't give us more, which is the problem, I think. How do we find other values? This is less than x, by the way. So we have the value of a single element. What does that help us with? Okay, maybe there's some other strategy. What if we don't find n? Or is actually, are there better ways to find n? That's the first question. We can find the value of the single element. We can do that in 2 queries. Does that help us at all? What can we do with this value? Like, say we get 1. That's not helpful at all. Because everything mod 1 is 0, so we don't get any information out of that. And 1 mod everything is 1. So that also doesn't help us. What am I saying? What am I saying? We can find the value of an element in 2 queries. What am I thinking? Wait, that's literally all we need. Okay. What am I doing? So the only thing we can't find a value of is n, because n is greater than anything else. So I think my strategy, I'm dumb. So the way we go is we do this. So let's say we have 1, 3, 2, 4, 5. And I'll underline something in red when we actually know its value. So we query between 1 and 3 with 2 queries, and we find the value of 1. But now we know 3 is unknown. So now we query between 3 and 2, and we find the value of 2. So 3 is still unknown. So then we query between 3 and 4, and we find 3. So now 4 is unknown. Then we query between 4 and 5 and find 4. So 5 is unknown. 5 is the only unknown value, so we know it's n. Similarly, if 5 is somewhere else in the array, this will still happen. 5 will always be unknown. So, okay, LL unknown equals 0. For I equals 1, I is less than n, I plus plus. Then A unknown equals n. Okay, well that could have been faster, but we're fine. So LLA query xy, LLYX equals query, wait, what is x and y? Unknown I, just call them A and B, I don't know. Query I unknown. So if A is less than B, then we know that B is the value we know. All right, let's call these B and C because I'm using A as the array. If B is less than C, then we know that I is the smaller value. So AI equals C. Otherwise, A unknown equals B, and unknown is now I, since we don't know it. Okay. So now we just test it locally, I guess. So let's do this. So we query 1 and 2, and we get 1 mod 3, which is 1. Query 2 and 1, we get 0. So now we query 2 and 3, we get 1. 3 and 2, we get 2. 2 and 4, we get 3. We get 1. 4 and 5, we get 4. And 1. 1, 3, 2, 4, 5. Okay, one more. We'll just do it with 1, 1, 4, 2, 3, I guess. So 1 mod 4 is 1, 4 mod 1 is 0, 2 mod 3 is, or 4 mod 2 is 0, 2 mod 4 is 2, 2 mod 4, or 4 mod 3 is 1, 3 mod 4 is 3. 1, 4, 2, 3. Perfect. And we submit to the right problem. Yeah, we were a bit slower on that one. That's fine though. Not doing too bad because we had a nice penalty on the early ones. Well, a lot of big deltas here. That's cool. Okay, we have 2 problems left. If there are n beautiful skyscrapers, the height of the ith one is hi. Today some villains have set on fire first n-1, now the only safety building is n. Let's call a jump from ith to jth discrete if all skyscrapers between are strictly lower or strictly higher than both of them. Okay. So if it's consecutive, it's just I plus, it's obviously that. So I guess the visualization here is that either they're consecutive, like obviously there's nothing in between, so everything in between is less, or there's some like everything is small, or everything is huge. And those are the 3 types of discrete jumps. Then we need to find the minimum number of discrete jumps it takes. So I'm guessing there aren't that many discrete jumps. No, never mind, there can be many. We can have something like this. So we have this, then huge, then less 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 huge. And all of these are discrete. So that doesn't work that well. However, so let's see. I think what's more important here is the fact that it has to be. Let's do some. Let's think about it like this. DPI is the minimum to get to I. The minimum number of discrete jumps to get to I. Then the answer is DPN, or DPN minus 1 if you zero index, which I'm going to. Then, let's say you're computing I, right? So there's some fixed number of stuff here. So as soon as we get to an element that's lower than this, or less than or equal, then actually, I think the way this would work is as soon as we get to an element that's so this jump is discrete. This jump is also discrete. This jump is not discrete. So it's not some interval, I guess. So what would be nice is if all of the discrete jumps formed some sort of like intervals, although I don't think that's true. What the hell? You just full solved. I don't think that's true though, that we can say that. So, what to do here? Something else that's kind of annoying is that, let's say we go through this, and now we're here. And now we're here. So then this one jumping from here is a discrete jump from that. And then we go to here. Now this stops being a discrete jump. But then it starts again. Or rather, forward. Okay. This is not easy, I would say. People are solving it. At least the implementation seems simple enough, though. Where's my mouse? So we think of some element. Then either the next element is equal to it, in which case that's the only jump we can have, it's greater than it, or it's less than it. Now if it's greater than, once we get to a different element that's less than it, like we're done. That's it. Nothing else in this range can be discrete because by default, the maximum is greater than this one already, and the minimum is less than this one already. So we only care about what's in between this range, actually. And how does this work? So let's say this is greater than this. Then we know that the only way we can get a discrete jump is where we have everything be greater than both ends. So if an element here, let's say we have some element here, and it stops being discrete. This element stops being discrete when we have some element to the right of it that's less than it. And I think that's how it works. This stops being discrete when we have some element that's to the right of it, and yeah. And of course, any element that's greater than it is totally fine because we need the discrete elements to be greater. So this element will permanently stop being discrete in terms of greater than when we have some element that's less than or equal to it. I think that in itself is enough. So we basically just take two cases. Either this is greater than this, or we have, like, for example, this, and this is less than this, and both of these are kind of like independent cases. What the hell? I just threw my... Okay, that was stupid. Then once we get to an element that's less than n, we're done. And then how does that work? We don't have an element less than n, that's perfect. Then we're just happy. The annoying part is equal elements, but I don't think it's that big a deal. So then that kind of becomes a segment tree query, where we're just interested in, essentially we say an element is still on if its value is, like if it works, and off otherwise. Then we just need to query the minimum of all on values in this range. And then we also need to query this element. think that should work. So essentially the only thing we need to do is we need to find the nearest greater than element and less than element to the left and right each time. It's going to be kind of annoying, but not that big a deal. I think the code should basically be the same. So how big the value is 300,005. It's probably overcomplicated, but whatever. So finding the nearest less than or equal to element is a standard problem, or you can do it like a stack or something. So le dot push, what would it be? It would be like how this works. So for less than, let's have some like -1, and gr dot push make pair. What is it? 2e9 -1. So now we do something like while le.size. Actually, we don't need to check that. While AI is greater than le.top.first, then essentially we have something like this. We have 7 and then 3 after it. And because this 3 is both less than and after the 7 is totally obsolete, so we can ignore it. And therefore we end up with a stack that kind of looks like this, where it's monotonic and like strictly non-decreasing. And the way that works is, then once we get like a 2 or something, we can kill all of these elements because we know that this 2 is going to be better. We can also kill this one, but it doesn't actually matter that much. Well, AI is greater than le.top.first, le.pop. Then less left I equals le.top.second. That's the index. Then dot push make pair of AI and I. And we do the exact same thing for the right, except it's less than because we're solving for the nearest greater element. So similarly, if we have something like 3, 7, then this 7 is both bigger than this and to the right of this, so this 3 is useless. Alright. Should be while le.top.first is greater than AI, I think. Yeah, because we want to kill all greater elements to the left. Then g.pop, or gr, whatever, greater left equals gr.top.second, gr.push, make pair AI. Now we do the exact same thing, but to the right. Then we do -1 in n, 2 in 9 in n, and the rest of the code doesn't change except for this becomes on the right. Okay. Let's just test this, just to be sure. Just test it on one of the samples. I don't know why they don't have an option to. Maybe they do, and I'm just dumb. So this should be -1, -1. Then this should be 0. This is the nearest last element. This should be 0 and 1. Yep. 2 and -1. Yep. 3 and -1. Perfect. That's perfect, right? Yeah. Test it on one more, I guess. -1, -1, -1, 0, -1, or 1, 1, 2, 0. That's right. Okay, now I'll just print to the right as well. Make sure everything works, just to be safe. This should be 5, 5, 5, 4. Yep, 5, 3. Um, 2, 3, and 2, 1. Yeah, okay. Sounds good. That's not what I meant to test it. 1, 3, 2, 2, 4, 3, 4, 4. I don't know, maybe. So there's some cool stuff you can do with like booleans where you basically just treat less than and greater than this as the same, but I don't want to do that because it's like kind of messy. Or it's not messy, but it's like kind of hard to get the details right in my opinion, so I don't want to do that. 2, 2, 1, 3. Less 4, 3. That works, right? Yeah, perfect. Okay, now we do the actual thing. So DP 300,005. So DP now we copy in a segment tree because we should. Then we want the minimum element. So it's a min tree. So we have two different segment trees. one for less than and one for greater than. Oh, I keep typing GE instead of GR. So now essentially an element is going to become invalidated once an element will become invalidated in terms of, like, say we're solving for something like this. An element here will become invalidated once we have an element less than it. So as soon as we have that, we're kind of screwed. And therefore each element will be valid in some certain range, and therefore we can do some sort of like 2 pointers to keep track of what's invalidated and what isn't. So that should work, I think. So let's do this. If AI minus 1 is equal to AI, then that is the only discrete jump we can make. So dp I equals dp I minus 1 plus 1. Once we finally compute dp, we say seg le dot update I dpi, and same for seg gr. Else, if AI minus 1 is less than AI, else. Okay, and then we just print the last value. Perfect. So now we just need to do the magic part. How do we do the magic part? Okay, so the way this is going to work is we're going to store a list of elements that we need to remove. We're going to store, like, 1 second. Basically, rem less and rem greater is going to store a pair of time to remove index, where time to remove is the position of the next greater and less element, and that should be fine. So rem less I equals make pair less right I and I. Then same thing for greater. Rem greater I equals make pair rem greater less greater. Wait. Greater right. Yeah. Then sort that I feel like there's definitely some better implementation we can do here. But this is what I came up with. Maybe there's some like observation-based solution, but nah, we're gonna just bash this out. So AI minus 1 is less than AI. Then we're interested in the position of stop equals. Essentially, it's the position of the next element that's greater. Because we're gonna have it's gonna kind of be like this, where we have this, and then we have some stuff here that's less, and then eventually we have something that's greater. And then this is gonna be a discrete jump, and nothing else is. And then like nothing else will ever be a discrete jump. So we only need to, so we can check this, and then we need to figure out what's on this interval and when it's valid. So we say L point, G point. Let me do some kind of 2-pointers. While L point is less than n and rem less L point dot first is strictly less than I, then it'll be invalidated. Wait, this should be, if this is less, if this is less, then this is only invalidated when we have an element that's less than this, I guess. Yeah, because it has to be a local maximum. So this should be rem greater, actually. Rem greater L point dot first is strictly less than I, then seg le dot update. This is the index itself. And let's just add infinity to it. That way it'll be way too big. Then stop equals we'll use I minus 1 plus 1 as a baseline. Then stop is the value of greater left. Then dpi equals min dpi 1 plus seg le dot query stop plus 1 I minus 1. That's just going to query this range essentially, and if something's invalid, it'll be like infinity, so that'll be fine. And then if stop is greater than or equal to 0, we can also get a discrete jump with stop, min dpi 1 plus dp stop. And now we do the exact same thing for this. While g point is less than n and rem less g point dot first is less than I, seg gr dot update rem less g point dot s rem less g point dot second and infinity. Add infinity to it. And plus g point. Then ll stop equals less left I equals min dpi 1 plus seg gr dot query stop plus 1 I 1. Basically the same exact code as last time. Stop. This we can copy. Okay, that is the basic idea. To do dot value. That's how my second tree works. What? Okay, this is sus. I don't believe this works. Let's try something big like this. Should be answer here should be 6. Seven, 1, 7, 2, 6, 3, 4, 3, 5, 4. Answer should be 1 to 7. I guess 5. Can you do it in better? 1 to 2, 2 to 3, 3 to 4. So 3. Yeah, never mind. 7, 1, 1, 2, 6, 3, 3, 4. Answer here should be 1 to 1, 1 to 2, 2 to 3, 3 to, so 5? 4. How do you do 4? 1 to 1. Oh, 1 to 3? No. 1 to 6? Oh, 6 to 4. Okay. No, 1 to 1, 1 to 2, 1 to 6, 6 to 4. Okay. I guess we'll try it. Seems right. We got it. Okay. It's not bad. I think we've lost a bit of place in the standings because people solved it faster, but that's not a big deal. I feel like we definitely overcomplicated the implementation. Definitely. But kind of interested to see what the easier solution would be then. Anyway, we'll try the later problem. N cities, N directed roads. Arbitrary directed graph. Arrive to city 1, travel to city N, give a constant and fly away. The two types of the roads in Dagestan. Yeah, black and white. Black roads are safe at night only, and white roads in the morning. Before the trip, the manager is going to make a schedule. For each city, he'll specify its color, black or white, and if during the trip they visit some city, the only time they can leave, it is determined by the city's color. Night if it's black, and morning if it's white. There should be no path from 1 to N, or the shortest path's length would be greatest possible. Okay. Interesting. Interesting. So it is a directed graph. Okay, so let's say we get to somewhere. What's the time limit for D? 2 seconds. Okay, that's fine. Oh, I have an OP room. Nice. how do we check if there is no path? Um, so each city's color is kind of independent of the others, kind of. I think if we get to some city I, and then if we get to some city I, there's no reason to like go back to vertices we've already visited, because then that's just a waste of time. So let's say we have how does this work? Let's say the distance to n is 0. Then we'll solve for all vertices that are adjacent to n. Um, that doesn't seem like it works. think we've somehow got to use the fact that the shortest path doesn't visit everything. I mean, it only visits a node once. So say we've ended up at node I somehow. Then we know the how does this work? Just kind of been walking around, not really knowing what to do. I think there's something interesting in the fact that all the colors are independent. Let's say we have some colors like, let's say this is city N. And we have, for example, some nodes like this, where they all have some edge to N, and then they have, I'll call these morning edges, like other places. So if some node has an edge to N of some color, then it has to be the other color. Like, no matter what, it has to be. But then what do we do? So if some node has an edge to n, then it has to be the other color. And therefore all of the rest of its edges are fixed. So now, for example, that all of these green edges have to exist. Let's say the starting place is here, for example. Then all of these green edges have to be fixed. So we can kind of do like a reverse type BFS from n, where first we fix the color of everything adjacent to n. Then we know that all of these green edges are going to exist. So then what? Then we, like this, like for example, this has distance 0. Then this has distance 1. And no other of these vertices have the potential to get distance 1. Because they don't have an edge to n. So the best path they can possibly have is somehow getting to this node. So I think we can kind of do the same thing for the edges that we still have. For example, we know here that this color is already fixed. But were it not fixed, like if this edge didn't exist, then the only way for this to happen would be to make this, for example, color black, and then we wouldn't get the screen edge. Anyway, I need to find some more formal way to visualize this, but I think I have the idea right now. It's kind of like a reverse BFS. So, vector so this is 2 and color. and we do some BFS. Or BFS. I guess we need visited? I'm not sure. Just to be safe. So now, it's like for each reverse edge, actually, basically if X can be either color, then we can fix its color right now. Actually, we'll only visit vertices whose colors are fixed. Because if someone's color isn't fixed, then that means there's no vertex that we got to where we had to fix its color. So therefore it doesn't matter what color it is. So we're going to assume the color is not fixed actually. V dot second is equal to color of X. I think even that is unnecessary actually. Yeah. So if not this v dot first, then color v dot first is equal to 0, then color v dot first is equal to X. Is equal to v dot second, and that's fine. V dot second. Otherwise, dist v dot f equals min dist v dot f. Then we have to visit that one. Q dot push v dot first. I think that should be it. Inf color is not fixed, then we can just make it whatever. Okay. Nice. Okay, what's with that? we have to make dist n minus 1 equals 0. Seem to be printing the opposite of the colors. Okay, that's fine. I think that works. Seems to work. Okay, we finished. Awesome. Where are we right now? 26th. Okay. That is a good spot. We have no penalties. I'm not sure if people will be able to overtake us. Oh, they might. This guy's done pretty well so far. These guys have A. Who else is in the running? We have like almost 6,000 points. And D is worth 1,200, and E is worth 1620. Okay, so my school starts at 12:30, but I did finish, so I do have time to go over all the problems. Let's do that right now. And I'm going to try and make it a bit quicker than usual, which means I'll try and keep them detailed still, but okay. Anyway, so let's do A. So I'm not going to read out the problems. I assume you have read them. And system tests haven't happened yet, so I can't guarantee all my solutions are right, but I mean, there have been a lot of pre-tests, so I hope so. So, firstly, for this problem, if you have an array of all zeros, you just win, because, like, there's nothing to add. The alternating sum is automatically 0. So if you have at least n minus 2 0, or n over 2 zeros, then just print all of those zeros. Otherwise, we know that the number of zeros is less than n over 2. Which means that, and since n is even, we can just do regular division here. That means what that means essentially is that n minus the number of ones is less than n over 2 as well. So the number of we can use math to figure out, like, we move the number of ones over here, move the n over 2 over here, and the number of ones is strictly greater than n over 2. And note that an even number of ones will also have alternating sum of 0. Because it's like, this is 0, the first 2 are 0, the second 2 are 0, the third 2, etc. So, since the number of ones is greater than n over 2, that also means that the number of ones minus 1 is greater than or equal to n over 2. So this is enough. If this is even, just print this. Otherwise, you can subtract 1. You'll still have enough ones, and you can make it even because one of these two numbers has to be even. That's basic number theory, or just like straight up mod 2. So yeah, any two consecutive numbers, exactly one of them are even. So that's basically it. If you have enough zeros, print the zeros. Otherwise, if the number of ones you have is even, print them. Otherwise, print one less than that number, and that should work. Or it does work. Not should. Okay. That's A. Let's do B. B is kind of, I don't know, unsatisfactory. So in B, you have an array, and you want to maximize the sequence of the prefix GCDs. So specifically, you want it to be lexicographically maximal. And what that means is that the first element should be as big as it can possibly be. Then once you do that, the second element should be as big as it can possibly be. Then the third, and then the fourth. which means you can kind of do greedy. Let's start the GCD off as 0. Then GCD of 0 and anything is defined to be itself, is that? Because I think, yeah. So let's start it by 0. Then we want to find an element that will maximize the GCD. So in this case, it's 8, because no other GCD can be as big as 8. So we take the maximum element, then we can't take this anymore. So now we need to find an element that maximizes the new GCD. And basically you can just greedily take, you can check all of the GCDs, and you can greedily take the element that, will just work. So, sorry, you can check all elements, you can find which one gives you the biggest next GCD, and then you can just take that one. And this greedy works because if you were to take some element that would give you a less GCD, it's not optimal. So you have to take some element like that. And you can also take any one, because no matter what, the GCD is going to be the same. So if there are multiple elements that you can pick that will give you the same GCD, then what you'll end up doing is picking all of those elements consecutively. So say you had 8, 2, and 6. So either the array would be 8, 2, and 6, or it would be 8, 6, and 2. Both of these are optimal because they both have the GCD array of 8, 2, and 2. So essentially, it doesn't matter what you pick as long as you maximize the running GCD. So the solution is to basically just go and greedy it. And because the constraints are small, n is up to 1,000, you can literally just try all possible elements for every single position, and that'll be like n squared log n if you use fast GCD, which is totally fast enough. So that's good. Now we go to C. Let's not close OBS. That's a good idea. C is fun, actually. I kind of liked it. It's cool to have a relatively simple interactive problem. So you're given a number n. There is a permutation. Actually, no. Sorry, I'm not going to read the problem. I don't have that much time. So let's first describe a strategy to get the value of any element. So let's say we have, for example, let's say we have 2 and 3. Note that because it's a permutation, all elements are unique, so one element is going to be strictly less than the other. So let's query both 2 mod 3 and 3 mod 2. So what's interesting? 2 mod 3 is 2, and 3 mod 2 is 1. If x is less than y, then x mod y equals x. Not by definition, but basically that. And y mod x, like by the definition of mod, y mod x has to be a number less than x. So if x is less than y, we can find the exact value of the minimum element between the two, which is essentially the value of the minimum element is the maximum of these two. And specifically, we can also use this information to find out which one of them is the minimum. So we can do that in 2 queries. Now let's assume we have this as a hidden permutation. 1, 4, 3, 5, 2. So let's use this strategy to find the value of one of these first 2 elements. Okay, so we use 2 queries and we end up finding that this is 1 and we don't know what this is. But now, since we don't know what this is, we can use this one in the later one. And so we can try again to find out the value of this by querying 4 and 3. So we take another 2 queries, this time we find out what 3 is. Then, so now we still don't know what this is, so we'll keep trying with it. And we try 4 and 5. This time 4 is less than 5, so we'll find out the value of 4. Now this is 5, and we don't know the value of this, so we'll try 5 and 2. 2 is less than 5, so in 2 queries we find out the value of 2. Then we don't know what this is, but it's fine because notice that we're going to find the value of every element except for n. Because every element will inevitably be matched with some element that's greater than it, because we have n in the array, n is greater than everything else. So therefore, the only thing we don't know the value for is 5. So we know it's n. And that's basically it. That's the permutation. So the way it works is we go along, we basically keep track of a single element that we don't know yet, and we keep comparing that element with subsequent elements until we find out every element except for one of them. And then we know that that one is n because everything else is less than n. So we would find out their exact values. Yeah, I think seeing my code would also partially help here, so I will link my submission in the description. Just check it out. I'll read that message after. Okay, this one is fun. I definitely overcomplicated it, since other people have much simpler solutions, apparently. Let's see, has my rank changed? It has not changed. Nice. One second. Just want to see how other people are doing. Why? What is this? Minus 48. What's he doing? Guess he's having fun. Anyway. Good job, Monogon. Doing better than me. So, now, what can we do? What can we do here? Okay, I'm not going to read out this problem, but here's the basic idea. First, we use a value dp I, which is minimum number of jumps to get to I. Okay. So initially, dp 0 is 0 because we started 0, and answer is dp of n minus 1. So how do we compute that? Let's say we're computing some I, and we'll leave I as orange. There are 3 cases. Either the previous value is exactly equal to the previous height is exactly equal to the current height, in which case this is the only discrete jump we can make. Because no matter what, the minimum and the maximum are going to be equal to this or worse off. So no matter what happens, in that case, that's the only jump we have. Another case is that this is this is greater than I. Then the thing to observe is that once we get to any element that's less than I, since we have an element that's less than I, or less than or equal to I, and an element that's greater than or equal to I, then no other jump to a point before this can ever be discrete. Because the maximum is greater than this value, and the minimum is less than this value. So we've already lost. There's nothing else we can do. So now all we need to do is somehow figure out the discrete jumps in this range. And we already know that both of these jumps are going to be discrete because everything in this range is strictly greater than this one, which also means it's strictly greater than this one. So this jump works. And we know this jump works because they're right next to each other. So which values in this range are valid? And essentially, because we know that this is greater than this, we know that, let's say we pick some arbitrary like other thing, we know that everything in this range has to be greater than both of them. Because otherwise we won't have a discrete jump. So, I'm running out of colors. So if we ever have some element that comes after this one, that's not this one, and it's less than or equal to this, then we're done. There's nothing we can do. We just can't make a discrete jump. So essentially, we can use this to jump off of until we have some element that's less than or equal. And basically, like, all we need to do then is find the nearest element that's less than or equal to each other element. This is a well-known problem and can be solved using a stack. I may go over that later, but not right now because I don't have much time. So it's just essentially it's called like the nearest less element or nearest greater element, and you can easily modify it to work for less than or equal to and greater than or equal to. So then we kind of do a two-pointers approach, where each value is kind of an interval where we'll be able to use this as a jumping place on L and R. So we activate this at L, and then we deactivate it at R. And this we can do with two pointers by sorting by R, and then we just keep a pointer along, and then whenever the pointer goes before I, we can remove this. That's kind of how it works. And then the way we get the minimum over all this is just with a segment tree, where if a value is deactivated, you set it to something like infinity, like 10 to the 9th or something. So you go through I in increasing order, then you keep track of the valid elements, and you essentially want to do a segment tree query of all active elements in the range between this element and the nearest less than or equal to element. And you can activate things with two pointers. And the other case where this is less than this is the exact same as greater than, but you just switch everything. So it's equivalent. I don't really need to go over how it works. Yeah. So essentially segment tree, two pointers. It works. Now we do E, and this is the final problem. So I'm not going to read it because it's kind of a long statement. But let's think about this. Let's think about all the vertices that have an edge to n. For example, we'll use black edges and green edges. Now, if we ever get to this vertex, like we very much don't want to take this. We very much don't want to take this edge. Because if we do, then like we're just screwed. We're automatically going to get to n in one move. So we have to make it so we don't have this edge. And therefore we fix its color to be black. And we fix this color to be green. And no matter what, we're screwed here, so it doesn't actually matter what this color is. It can be either. So now we know that this can't get to n, so its distance is basically infinity, and this can't get to n, so its distance is also infinity. But this, no matter what, does get to n, so it does get to infinity. So now we treat this like vertex 0. And then we look at all of the edges that go into this. We look at all the edges that go into this vertex. Now, by the same reasoning, we can fix the colors of these vertices to be the opposite of these edges. Because say the color is this, but then there's some other path that's shorter. But then if there's some other path that's shorter, by like the BFS argument, and the reason why BFS is correct, we would have seen it before. Like we would have, if this edge existed, we would have considered this edge in a previous turn, but we didn't, so there's no shorter path. So these edges that lead into this visited vertex it leads to the shortest possible path from this vertex. So these colors have to be the opposite. And of course, maybe there are some other edges among this, but it doesn't really matter because there's no way for these vertices to get to any other vertex that we've done. And if there are multiple vertices with distance 1, then, like for example, like this, then we just do them like separately. And if we have, let's say for example, we have this. So this is, let's say these blue edges are forced. So this vertex has distance 0, it's n, this has 1, this is 1. So now we have some vertex here. And we have an edge from this to both of the 1 vertices. However, this doesn't really mess up implementation, because here, let's say we look at this vertex first. Then here, this color has to be green to avoid getting to this 1. So now we say it's infinity, but then later we look at this vertex and we say this color has to be black, but it can't. So we can just not change its color, and then we end up visiting this vertex, and we consider all edges that go into this. So it's kind of like a BFS, but on the reversed graph. And then we greedily fix the colors to minimize the shortest path to every vertex individually. And then if this greedy process ends up stopping at 0, then we print the distance to 0, otherwise we don't. So if you think about it, it's a lot like reverse BFS. And you never need to visit vertices that are at distance infinity because you just don't care about them. Like, there's no point in ever visiting this vertex because you'll never go to this vertex in the optimal solution. Yeah, so again, much like a BFS would, you would visit all vertices with distance 0, then all that are forced to be distance 1, then all that are forced to be distance 2, and etc. Until you either get to 0 or you don't, and then you print the answer and print -1 if the distance from 0 is infinity. That is it. I know I kind of rushed through this because I don't have that much time. Normally I'd be able to go into, I guess, more detail, but I can't right now, so I'm sorry about that, but hopefully it's still, like, understandable, at least, how everything works. I basically gave a brief idea of... Wow, he beat me by 12 points. Okay. Basically, we have a brief idea of... I gave a brief idea of everything. I've beaten in the IGMs. I have to have. There we go. Okay. Yeah, this is basically Speed Force. Well, no, not exactly. I mean, at this level. But that is basically it. That was round 669, and those are the solutions. So again, for D, you can search up how to do nearest greater element. I'll leave a link in the description. I'll also leave my code, specifically my submissions, so you can check everything. And okay, that's it for me. See you guys.